Welcome to the session. So today I am here to explain deletion operation on binary search tree. How to perform delete operation on binary search tree. In the earlier session we discussed insertion operation and search operation on binary search tree. So first let us recall binary search tree operations. So in the binary search tree operations, say the first one is insert, the next one is, this is completed, the next one is delete. So in the deletion case, 0 number of childs, such type of nodes are called as leaf nodes, and a deleted node having 1 child and deleted node having 2 childs. So the search operation is also completed. So first manual example, say this is a tree. So here 45 is the root node, 39, 56, 12, 54, 78, 10, 34, 67, 89, 32. So here the first case 1. Case 1 is 0 childs. 0 childs is nothing but leaf nodes. 0 childs is nothing but leaf nodes. So say for example I want to delete an element that is 32. I want to delete an element that is 32. So in that case simply 32 is deleted automatically. Means here the left pointer is make it as null. The left subtree is make it as null. So it's a very simple kind of operation. It is a very simple kind of operation. So at the time the resultant tree is 45, 39, 56, 12, 54, 78, 67, 89, 10, 34. This is the resultant tree. So, case 2 means 1 child case. Say for example 1 child case. Suppose I want to delete 39. What is the child? The child moving to that particular position. What is the child having to that node? Automatically the child comes into the particular position. Means say 45, 12, 10, 34, 56, 54, 78, 67, 89. So when we are removing 39, automatically 12 comes to the respective position. So the next case, continuation. Say this is very important case. Case 3 means node having 2 childs. Node having 2 childs. Suppose I want to remove the root node 45. Suppose I want to remove root node, say that is 45. So here 2 possible options are there. The 2 possible options means, here the first ambiguity is, whenever we are deleting the 45, whether left child becomes the root node or right child becomes the root node. In that case, how to balance the tree? Balancing is nothing but the resultant tree should be satisfy binary search tree property. What is the binary search tree property? Comparatively root node, lesser element as a left child, greater element as a right child. So here 2 possible options is, say this is a left subtree, this is a right subtree. 2 possible options are, in 2 different ways we can balancing that. So by considering left subtree, by considering right subtree. Okay. So whenever we are considering the left subtree, so in the left subtree, the maximum element is replaced in this position. Left subtree maximum element we are replacing in this position. So what is the maximum element in the left subtree? Maximum element in the left subtree. Just verify. 39. 39. The maximum element in the left subtree is 39. Okay. So this is called as IInd predecessor. IInd predecessor. So in that case, what is the resultant tree? The resultant tree is, so the first 39 comes to this position, 45 comes to this position. So 45 comes to this position. Means these two are interchange. In our technical terms, we can call it a swap. The next 12, the next 10, 34, 32. Here the part is not changes. So 56, the next 54, the next 78, the next 67, the next here is 89. Here the 45 is deleted. Here no ambiguity. Why no ambiguity? Means only one child, automatically 12 comes to the 45 position. That is clearly seen in the previous case. So this is the case of IInd predecessor. So one condition is clarity. What is the clarity is? Here the balancing node is either left subtree maximum node or right subtree minimum node. Definitely the left subtree maximum node having either 0 childs or 1 child. Or in case of right subtree minimum node having either 0 childs or 1 child. So this is the IInd predecessor case. We will see in the IInd successor case. We will see the next case is IInd successor. So IInd successor means right. Just now I told that. So the right subtree maximum element. The right subtree maximum element is 89. Means we need to start these two. Means say 89. After that 39, 12, 10, 34, 32. Here 56, 54, 78, 45, 67. Means we need to swap these two. Just we are swapping these two. Later, what happens is the 45 is removed as a 0 number of childs. This is the resultant. So here property is also automatically satisfied. What is the property? Comparatively, sorry, here the one wrong is there. What is the wrong is? We need to map with minimum element, not maximum element. Sorry, we need to map with minimum element. So what is the minimum element here? 54. So here 54, 54, 54, the next is 56 here, the next 78, the next 67. Okay. So the 67. So just this 54 and 45 is swapping each other. So here 45, here 54. Automatically it is balanced. So comparatively all the nodes 54 is the greater one. Comparatively all the nodes 54 is the minimum one. So here 54, 45 having 0 childs, simply it is deleted. This is the case of in-order successor. This is the case of in-order successor. Either we can get maximum element in the left subtree, that is in-order predecessor, or we can find out the minimum element in the right subtree, that is called in-order successor. So how to write a code for this? So this is the code. Say first, whenever we want to delete it, so we need to write return type things or cannot write also. Means here say struct. Actually we are called it as BST node. Okay, star, that is the return type. Delete is the function. Here we are using recursion. When we are using a recursion, compulsory we need to pass the root node address as an argument in the first iteration. Means BST node star, say T, that is maybe root node. Next, value. What is the value we want to delete it? That is always integer, so say int x. This is an algorithm. How to convert the algorithm I will tell you. So the first case is, if, this is we know that, if t double equal to null. So when the t double equal to null, it is empty. So the t is empty. Means we can't do anything. So here we can write the tree is empty, value not found. So not found also. In that case, not found also. Else if, this is not the case. Else if. So else if, what is the condition? So we are passing value, say x. X less than tree of data, means a t of data. See here, completely verify comparatively root node data element. X value is less. Means that we have to move in the left subtree. We have to move in the left subtree. Means that simply what we have to do is delete t of left, and we are passing x. T of left comma x. Suppose not the case. Else if means we need to check x greater than t of data. X greater than t of data means that compared to root node element, our required element maybe is in a higher position. We want to move in a right subtree position. Means delete t of right comma x. Means we want to go for right subtree. So these two things are not there. Means not less than, not greater than, not null. Definitely it is equal to. We no need to check it. Means that element is found. So else case is nothing but element is found. This is element not found case. This is the left subtree moving case. This is the right subtree moving case. These three cases are not possible. No doubt element is found, but we need to check the element having either 0 childs or 1 child or 2 childs. So that's why here we are checking that temp of left and temp of right. Means if both the values are not null, okay, not null, so we need to check else if t of left and t of right. So t of left not equal to null, t of right not equal to null. That is what it means is. Null means 0. 0 means false. So here we need to check and. And means we are using logical and. Okay. So in that case what to do? First to find the largest one. Say here I am calling it as say f. Find the largest node. Largest node means they are following in-order predecessor case. In-order predecessor case. So IP. In-order predecessor means IP. So we need to check in the left subtree. So left subtree means we need to pass left subtree address. we need to pass left subtree address. The next one, what we have to do is, first we need to swap. So, T of data is equal to F. Our required means our deleted node address is T. So, T of data is equal to F. Means initially we are keeping our largest element is in that particular position. Later, what we have to do? Call the delete function. Where we are getting that element? Left subtree. So I am passing left subtree, T of left comma. What is the element? F. I am calling again delete function. I am calling again delete function. Suppose that is not the case. That is not the case. Go for else. So this is two child case is over. Then next remaining things are one child case, zero child case. So we need to check one child case first. Okay. Then later we will check zero child case. So just check T of left equal to null, T of right equal to null. Means zero child case. Zero child case simply we are removing that. So removing means 3 is equal to null. Just set as null. Automatically it is deleted. Suppose not the case, we need to check one child case. T of left not equal to null means left child is there, right child is not there. So we have to move the left child case. Means that T is equal to T of left. Convert case. Left child is null, right child is not null, means T is equal to T of right. So this is the deletion code. This is the deletion code. First I am checking that T is equal to null. If the T is equal to null, whether maybe bind the tree is empty or maybe position not found. Why? Because recursively we are moving. At any position we are getting null, means in the particular path element is not found, means that element is not found. Okay. So whether it is in the left subtree, we have to move in the left subtree. Whether it is in the right subtree, we have to move in the right subtree. Suppose both the cases are not there, whether the element having means element is found, the element having two childs. So in the two child case, we need to find out another predecessor and swapping the nodes. Then we are removing that particular node. Not but case, zero childs, just T is equal to null. One child case, whether left child is there, left child we have to set, right child is there, right child we have to set. So, what are the functions we are using to find out in-order predecessor and in-order successor? These two are the codes. Say for example, int. Okay, find the largest element, nothing but in-order predecessor. We need to pass struct BST node star, or simply you can call it as BST node star T. So here we need to check if T double equal to null logical and T right, T of right, okay, T of right equal to null means return T. Say suppose T is null or T of right is null, simply return T. Else if, not else. So return recursive call. So in-order predecessor of T of right. Why? Because here we need to find the largest element. Largest element in the left subtree, right position is there. Left position always minimum to the particular element. Okay. So that's why we are moving to right position. Convert case, we need to find the smallest element. So in-order successor, IS. Here also we need to pass BST node star, say T. Again here also we need to check if T double equal to null, logical R. Say logical R means, this is the case, logical R. So T of left double equal to null In that case, return T. Else, convert case. Simply we need to call recursively. So return of IInd successor of, we need to call left element. So left. So these are the codes used to find out in a left subtree maximum element IInd predecessor or in the right subtree minimum element IInd successor. The next, this is a very important question. So many number of times they are asked how to calculate the height of the binary search tree. Say here, how to calculate the height of the binary search tree means, say this is the 0th level, this is the first level, this is the second level. At the time 3 levels are there, height is 3. In that case, maximum level plus 1. Or we can start with 1, 2, 3. So simply you can write binary tree height is 3. Okay. So how to do code for this? So here also int. So height. So height. We need to pass BST node star T. Initially we are passing root node. Recursively we are moving to last position. So if so T double equal to null, so return 0. Means in the leaf node case, we need to consider this. Else, we need to check. So int left height LH is equal to height of T of left. Recursive call. Int right subtree height is equal to height of tree of right. We need to check which one is maximum. Say in this case, right subtree is maximum, left subtree is minimum. So left subtree height is 1, right subtree height is 2. So 1 comma 2, maximum is 2, 2 plus 1, that is the resultant tree height. So like that here, each and every case we need to check the height of the left subtree and height of the right subtree. So if left subtree height greater than right subtree height, what to do is return left subtree height plus 1. Why? Because in this case left subtree height is more. In other case, return right subtree height plus 1. So this is the code for calculating the height of the binary search. Similarly, we can calculate the total number of nodes in the tree. Very easy. Initially we are passing the root node address. If the t value null, 0. Not null, total number of nodes t of left plus total number of right plus 1. So majority of the codes in the binary search tree we are using recursion only. With the help of recursion we can write codes very easily in the binary search tree. Next, the very important point is go for tree traversals. We already listened the traversal term in the single linked list and double linked list. So traversal means what? What are the elements we are inserted in the particular linked list? Just display. Similar way, in the tree case also, what are the elements which are inserted in the tree? We need to display it. So for displaying purpose, here 4 type of traversals are there. 4 type of traversals. So traversing a binary tree is a process of visiting each and every node in the tree exactly once in a systematic way. Linear data structures in which elements are traversed sequentially means like a straight line fashion. In a straight line fashion. Okay. So a nonlinear data structure in which elements are traversed in a many different ways. Nonlinear data structure means different kinds of paths are there. So we can travel in different directions. So here, in order is there, pre-order is there, post-order is there, level order is there. So in case of in-order traversal means initially visit the left subtree, left subtree, then visit the root node, then right subtree. In pre-order case, visit the root node first, then left subtree, then right subtree. In the post-order case, initially visit the left subtree, then right subtree, at last visit the root node. Level order means level wise we are visiting the nodes. Means 0th level nodes first, first level nodes next, second level nodes next, like that we will reach end of the tree. So how to find out the in-order traversal for this node? So in-order traversal means what? First visit the left subtree, then visit the root, then visit the right subtree. So just concentrate, this is a very simple logic. First visit the left subtree, then root, then visit the right subtree. Here also same, recursively. First visit the left subtree, then visit the root node, then right subtree. Here also, first visit the left subtree, then root node, then right subtree. Here also, first visit the left subtree, then visit the root node, then right subtree. So what is the first node we are visiting here is G. First we are visiting G, followed by D. Why? Because D is the root node. Followed by, again left subtree. Here left subtree is not there. Then root. Root is nothing but H. Then right subtree means L. Then next case root node B. Then visit the right subtree E. Completed. Then visit the root node. Say A. Then visit the right subtree. In the right subtree, what is the first one? Here. Here we need to go for left subtree. So left subtree is not there. Means C. Then go for right subtree. Means this one. Before this one, left subtree. So I. The next is F. F. Next. Subtree case. Means K. Followed by J. So visit the left subtree, then root node, then right subtree. This kind of traversal is called as in-order traversal. Next, pre-order traversal. So in case of pre-order traversal means first visit the root node, then visit the left subtree, then visit the right subtree. So in the total case, first root node is A, means we are visiting A first. The next left subtree. In the left subtree again root node is B. So that's why B. In the right subtree, the root node is C. But initially finish all the nodes in the left subtree, then only we will go for right subtree. Okay. So recursively case. So again in the left subtree, what is the root node? D. So here D. Again here recursively, root node G. G. In the right subtree, root node is H. So H. Here L. So L. Next we will move for E. So the next is E. Again next, this is the case. C. Next F. So F. Next this is I. So I. Next this is the case. Then go for J. After that. So here the path is first visit the root node, followed by left subtree, followed by right subtree. Finally, this is the last traversal. So post-order traversal. In the post-order traversal, very simple logic is first visit the left subtree, then visit the right subtree, then root node. So that's why we are getting root node in the last case. And level order traversal. So level order traversal means first visit the first level node A, next visit the second level nodes B, C, next visit the third level nodes D, E, F, next visit the next level of nodes G, H, I, J, the next visit the next level of nodes L and K. So how to write the codes for these three traversals? And here very important question is, sometimes they are giving two different traversal and construct a binary search tree. That kind of questions also may give in. So how to construct the binary search tree, we will see in the next class. So in this class, first we initially go for what are the concepts we have discussed till now. So first, deletion function in the binary search tree we have discussed. First, deletion function in the binary search tree. Here three different cases are there. The three different cases are 0 childs, 1 child, 2 childs. Here in the 2 child case, two possibilities. One is in-order predecessor, another one is in-order successor. In the second case, we need to write the codes for in-order predecessor, in-order successor, along with the delete function. Along with binary search tree delete function. And third one, we are going to know about traversals. So in the traversal case also, 4 different kinds of traversal we will see. One is in-order, another one is pre-order, third one is post-order, last one is level order. So these are the topics we have discussed in this session. In the next section, we will discuss how to write the codes for these 3 different kinds of traversals: in-order, pre-order, post-order. And in the reverse way of construction, while they are giving in-order and pre-order, how to construct a binary tree. Also we will see in the next session. Thank you.